we look at is how optimizing compilers can remove code which is so-called dead code. And dead code is code that is not reachable, for instance. And such code can be detected using depth first search. And in fact, Tarian's algorithm to construct the dominated tree starts, during its depth first search, it discovers nodes that are not reachable from the beginning of the function, and they clearly can be removed. And an example of that would be this printf, since it's skipped, so it is not possible to go there. Another approach to to dead code elimination is to see if a variable is used in the future. Okay, so without this goto, the A would be used here, and therefore it cannot be removed. But since there is a goto here, this A is not used in the future, so why compute it? We can actually skip it. Okay, and then now this A is not used either, so we can skip it as well. And then this one will disappear. So what is done is, or not is done, but could be done, or was done rather, is to see which variables are live, and those which are not, we can remove their assignments. And that may make some other variables useless, and we can remove them as well. But that doesn't work perfectly. If we look at this, this is what is needed, but this is still in the code. And in the basic block. Okay, so it's still there. And if we look at this I, it is used in the next iteration. So we want to remove all of this, but liveness, okay, I didn't say liveness analysis, what it is, but it is the analysis to determine if a variable is used in the future. So that doesn't really work perfectly. Another example of that is this loop. Since both I and A are used in the next iteration, we cannot remove it. Okay, but why keep it? Okay, so dead code elimination based on DFS. That's perfect. It's done in the dominance analysis, but this one is not so suitable to use. Okay, so what should we do instead? Well, what we should do is to remove everything that does not affect the visible output of the program. Okay, but recall from the lecture on for loops and loops in general. If we have this loop 1 and then do nothing and then abort, this was not clear what the C standard meant by this, if a compiler is allowed to remove this loop. Clearly it has no, well, it depends on how you see it, but the statements within this loop, they do not affect the visible output or observable output. So removing everything that does not affect the observable output it would actually change the observable output of the program, since now we would leave this infinite loop and come to this abort function and terminate the program. Okay, this was clarified in C11 to mean, I mean, it says that if there is a non-zero constant loop condition, then that loop is not to be optimized away, even if it doesn't affect output. So, what is to do now? Well, okay, considering that we have this rule, but that's an exception, we can say. But dead code elimination based on observable output works as follows. First, we mark all statements that can affect output. And what can affect output? Well, clearly a call to printf or assignment to a global variable, not the local variable that will disappear anyway when we leave the function, but the global variable. And the reason for marking assignment to global variables is that we don't know usually how they will be used in the future, so we must be conservative and assume it may be used in the future. Okay, so function calls, usually they are removed as well, but not necessarily all. For instance, if it's a call to a math function that is known to have no side effects and not called printf, for instance, then such calls can be removed as well. But in general, function calls, writes to memory, that means through a pointer or global variable, and return instructions, they are marked as live. Okay, and then the operands to these instructions are also marked as live, etc. So eventually we will have marked all instructions that can affect output as live, and the others can be removed. It's quite obvious that this is how to do it, but why did it take 30 years to invent this approach? It was actually published in the same journal article as SSA form. And as a matter of fact, the details of translating to SSA form are very similar to how this special aspect of this algorithm is done, except that the dead code elimination, it uses the reverse control flow graph. Well, this is just to mention this for a curiosity, that was a very interesting paper. Okay, so well, it's this one. This is the journal, and okay, so I will now come to what complicates this. Well, as I have said so far, this dead code elimination is just about marking instructions and their operands and continue. But there is another concern that complicates it. But well, okay, let's look at this first. And okay, so what we do is to check if a statement can affect output, such as is it a call, function call, return, or write to memory. Then we set it to be live. Otherwise, we do not say it's live, and if it was live, we put it in a work list. Okay, so what we do then is to go through this work list and mark operands and put them in the work list as well. Okay, now we have something down here, and I will not go into the details, but what we will need to do is to realize that some branch statements must be marked as well. Okay, so say we have well, we can say that we have a printf here. We cannot just let, so here we have hello world, and here are some if statements. We cannot just let the start statement branch there. I mean, we don't know if it should, but what we need to do is to mark branches which control whether this basic block or node with the printf should be executed another time. Okay, so which are those? The branch here, so here will be an if in the source code, since there are two options, and this one can decide or control that W will be executed another time or a first time. So this one should be marked as live. Okay, next question, should this one be marked as live? No, because it will not determine whether W will be executed or not, since regardless of whether we go there or there, we will come to W. So there is no point in doing this if just to determine whether we should use the printf there. So this one is not marked as live, but this one is live, so we can mark it as red. Okay, is there something else here? There is no if, so nothing happens. W, it can loop back to itself, so it certainly can determine that it should be executed. So that one should be marked live as well. And then this should also, since it can decide to go to Y, which will lead to W, but the others are not needed. And what we do is to say that W is control dependent on U, V, and in this case itself. Okay? So this is what is done here, and so what the algorithm does is to compute a certain set of vertices which control whether this one should be executed or not. Okay, I will not go into the details how that is done. That is covered in the optimizing compilers course, and well, these branches are marked and put into this as well. Okay, and what we do then is to simply remove all statements that were not marked as live. And but I should say we keep the first instruction in every basic block and all the branches. Okay. And what we should do then is to simplify the branches and skip some nodes in the control flow graph. So I will not talk about the details in this one, but I will just illustrate what the idea is. So say these green are marked as live, and we should branch. I mean, we should keep them. So this branch should, and I mean the black are not, they should not be preserved. So this branch should not go to 2, but instead, instead of going to 2, it should go directly to 3. And from 3, we should go directly to 7. Okay, and that can be done in something which is similar to the dominator tree, but in the reverse control flow graph. Okay, I forget about the details. I mean, I have not said them, but they are here to make you fascinated by this nice topic. Okay, So what we see is that, okay, I will skip these details and just show what happens. We go there, and then the other one will go all the way directly to 7 instead of going to 9. Okay, and then both cases for, 3 had 2 successor vertices, 4 and 8, and both of them will end up in 7. And of course only one is needed. Okay, but so this is how dead code elimination on SSA form works, and it was introduced in 1991. And then we can do another depth first search and remove all the vertices that are not needed.